Swayam Prabha. Digital India. Educated India.
All right, so let me continue. So you see, we are trying to give an introduction to differential geometry, at least what this course is going to cover, and I have told you some interesting things about curves. Okay, what I want to tell you next is about some interesting things connected with surfaces. Okay, these are all related to some important theorems we are going to prove in this course. Okay. And so let me right away start by writing that down. Surfaces. So I will just write it as differential geometry of surfaces. So you see, of course, the fundamental question you can ask is, how do you approach the differential geometry of a surface? Okay, we are going to think of the simplest case of surfaces, namely surfaces sitting in 3 dimensions. So you are going to look at things like spheres and cones and cylinders and things like that. Okay, and of course conicoids like hyperboloids, ellipsoids, and so on. Okay, now of course there is a fundamental question: how are you going to make sense of curvature of a surface? Okay, that is somewhat a little bit more technical. Okay, and the brief answer to that is that we try to approach the idea of curvature of a surface by looking at the curvature of curves on the surface. Okay, so you build up the theory of curves, the differential geometry of curves, which is essentially trying to get the curvature of curves, understand the curvature of curves. Then what you do is that you have curves on surfaces, you start measuring the curvature. Okay, and then the idea is that as you measure all these curvatures of various curves on the surface, you should get an idea of the curvature of the surface. Okay, so that's the brief answer, but I will go into it in more detail soon. Okay, but let me tell you a couple of interesting theorems which are directly connected with this, and which are also very curious. So let me write this down. How to measure the curvature of a surface. And the answer to that brief answer is use the curvatures of curves lying on the surface. So that is one aspect. The other aspect is interesting theorems, interesting results, and I will put, they are also theorems on surfaces. Of course, there are many results, but I want to classically only talk about a couple of them. Okay, they are known as the Gauss-Theorema Egregium. Okay, and the so-called Gauss-Bonnet theorem. Okay, they are both due to Gauss. Okay, and they are amazing theorems. So let me talk about. So let me write that down. So Gauss Theorema Egregium and the Gauss-Bonnet theorem. So let me tell you something about the Gauss-Theorema Egregium. So this is Latin for egregium is Latin for remarkable. So this means remarkable theorem. And but in words it looks like a very obvious result, a very simple result. Okay, But then why would Gauss call it very remarkable? Because if you get into mathematically proving it, you see some remarkable things happening, okay, and we will see that in the course, okay. So what is the theorem? The theorem is a very simple statement, is very simple in an intuitive sense, that no portion of the sphere looks like a portion of the plane, okay. So let me write it like this, loosely, no portion, or let me say no region on the sphere looks like a region on the plane. Now, so you see, the statement looks very silly. No portion of the sphere looks like a portion of the plane. If you say something like that, then anybody will say, well, it's obvious, because you see the sphere is curved, the plane is flat, and so certainly that's true, okay. But actually the curvedness of the sphere is very large, is something that you don't directly see. For example, we live on the surface of the earth, and for all practical purposes it seems like we are living on flat land, okay. Of course it is, it's only when you make when you look at the shoreline, or you look at the sea in the horizon, then you see that there is the curvature shows up somehow, but otherwise you don't feel it, all right. So, and on the other hand, if you take it at smaller scales, if you take a ball and if you take a flat piece of cardboard, then they are obviously different, okay. But now again, mathematics has got to do with not just being satisfied with the intuitive statements. You want proofs. The question is, how do you prove this? I mean, I want to really take a suppose I take an open region on the sphere, and I take an open region on the plane. So both have some surface area, and they are open in the sense that I am not worried about the boundary. They are open sets in the sense of topology. And suppose for the moment you took connected pieces, then no two such pieces can be they cannot look the same. They cannot. So the point is, what do you mean by look the same? Of course, you have to involve curvature, because if you don't involve curvature, then you can flatten a portion of the region of the plane on the portion of the region on the sphere, and make it look like a portion on the plane. The only thing that's distinguishing is curvature. So the question is, how do you get a hold on curvature? And I told you curvature is the second derivative. Therefore, you have to use calculus. So you have to bring in this curvature into the picture. Okay. Now, how do you do that? So that's where differential geometry comes in. So what I want to say is that this if you write this as a theorem, then this is the great Gauss Theorema Egregium. Okay, and the greatness is in partially trying to formulate it perfectly mathematically. Then of course in trying to prove it, okay. So let me say something about, so this is connected with, so what are the applications of this? The applications of this are cartography. So there is this field. So what is this cartography? This is the the science, or the you can call it a science or art, whatever it is, of having maps, okay. So this is the it's creating maps, all right. And normally what do you want a map to do? So you want maps to do a couple of things. The first thing is that if you want so that, of course I am talking about a map of places on the earth, okay, and I want a map that is not I mean that that's on a piece of paper I can fold and carry it wherever I go, okay. So basically you see the problem is already there. I am trying to represent something that's curved, the surface of the earth, on something that's flat, which is a piece of paper, all right. And then the net answer to all this is that you cannot do it, okay. So Gauss theorem Egregium says you cannot do it accurately, okay. So what really goes wrong? So this, trying to understand this question is very much handled by differential geometry, okay. So let me tell you what you expect of a map to do. So the first thing is, maps can ideally be So I will write out 2 or 3 aspects or characteristics. So what you want to have in a map is, the best thing that you want is, suppose I have 2 places, they are marked on a map, then I want to be able to measure the distance between them in a nice way. Of course, normally when you look at a map, for example, you look at Google Maps these days. So when you look at some region or some neighborhood, then it gives you a scale. It gives you a scale saying that this much on the screen is like 200 meters, or this much on the screen is like 1 kilometer. Okay. Now you can use that to actually measure distances. Okay. So a map which is scaled, usually there will be a scale to a map, and if you have 2 points on the map and you want the distance between those 2 points, then you find the actual distance on the map and then multiply by the scale, and that should give you the actual distance in real life. Okay. So if I want the distance from, let us say, Chennai to Hyderabad, then I measure Chennai to Hyderabad distance, which is probably a few centimeters, and then multiply it by a scale factor. Every centimeter is perhaps several hundred kilometers or hundreds of kilometers, and then you multiply by the scale factor, and then you get the the distance. Okay. Now, so the first thing, so I will write this. These are distance preserving. So distance preserving, so you accurately are able to get the distance between various points. Then the next thing that I would like to have about maps is give directions correctly. Okay. So I should know that if I am in, let us say, Chennai or Madras, Hyderabad is roughly due north of me, and Mumbai is so let's say due north west, and then to my west is Bangalore. Okay. So you have these directions. So you want a map to give give directions, gives directions properly. And the third important thing that you can expect of maps is to represent areas correctly. Okay. So this is more technical when you come to various large scale phenomena. For example, if I want to calculate how much of sun's light is falling on, let's say, a portion of the earth, okay, then I need to know what is the area on which it's falling. Okay. If there is rain in a certain area, okay, then if I want to know what is the density of the rain that's falling, then I need to know the area where it's falling. Okay. And so these are, for example, if I want to know how much area is under cultivation, then using satellite imagery you can spot which are the regions which are cultivated, and then now you have to measure that area, the regions which are green. Okay. So you need to measure area. So you also expect a map to give areas in a nice way. So so let me say, I said maps, so I should say give. So give direction properly, give areas properly. Okay. Now you see, these things can be made in sense of mathematical. Now maps that preserve distances, there is a special name for them. They are called isometrics. Okay. So metros or metric is supposed to be distance, and isometry is, isos means equal. So isometries are things that preserve distance. So you want maps that are going to preserve distance, and they are called as isometries. Okay. So the maps that preserve distances, they are called as isometries. Okay. And the maps that give directions properly, there is a name for that. So how do you think of it? Basically, suppose I have 3 cities. Okay. Then you join these by straight lines, and then you can say what is the angle between these directions. Basically, the idea of giving a direction is to have a fixed direction and say every other direction is at a certain angle to this. So basically, you see, you are measuring angles. it's angular measure. So giving direction properly is supposed to measure angles. And the maps that measure angles properly, the word for that is, the technical word for that, they are called quasi-conformal or conformal maps. Okay, so let me write this down. So let me write it. Quasi, I'll put the quasi in brackets. Okay. Now, of course, there's also the other word, which is equiangular. Okay. So basically, what these maps do is that if you give me 3 points, okay, then you take one point as fixed and join the other 2 points, and then you get the angle between these two, segments. Okay. So of course, when you measure the angle, you can measure every angle in 2 ways. Okay, either clockwise or anti-clockwise, and then you can also worry whether you are measuring it in the right sense. Okay, and because there is the only difference is by a reflection, okay, which can change the sense. So if you are not worried about the sense, but you are worried only about the angular measure, then that is what is called as quasi-conformal. Okay, if you are really worried about also the angle, the sense, whether you are measuring positive in the positive sense or negative sense, if you want even that to be preserved, it's called conformal. Okay, so in any case, you want maps to measure angles properly. And then the third thing is, of course, give areas properly is something that makes sense. So the name for this is what is called as equiareal maps. So equiareal maps means there are 2 maps, and then there is a region. For example, if you have a map of the earth which is equiareal, then you take a portion of the earth on the map and measure the area as given by the map. That will actually correspond up to a scaling factor to the right area on the surface of the earth. Okay, so they are equiareal maps. Now you see, what happens is that if you are doing ordinary geometry, okay, we see this even when we study congruence, of triangles and so on, when you do plane geometry, let us say. So you know that in plane geometry, okay, what happens is that if a map, so let me first say it in a very simple way. If 2 triangles are congruent, then you see immediately they have the same area. Then you also see that they have all the angles equal. So what you see is that an isometry. So if the 2 triangles are congruent, it means all the sides are equal. Okay, that the lengths are preserved. All right. So basically, this means that you have an isometry, and then you see if it is an isometry, then you see that it is also conformal. It's also equiangular or quasi-conformal, and it is also equiareal. It also preserves areas. Okay. So in plane geometry, you see this. So let me write this: isometry. This implies equiangular. So let me write it as equiangular and equiareal. Okay, and you see, on the other hand, suppose you have only something that's equiangular, then it's a similarity. If 2 triangles have the same set corresponding angles, then they are just scaled. It's just one triangle is scaled by the other. Then what happens is that the distances are scaled, but the areas are also scaled. But so what about this map? This map is actually going to be equiangular, but not equiareal. Okay, and therefore it's not an isometry. All right. So if it is equiangular and not equiareal, then it is not an isometry. But suppose it is equiangular and equiareal. Okay, if it is equiangular and equiareal, suppose I have 2 triangles which are similar and have the same area, then they are congruent. Okay, so equiangular and equiareal will force isometry, you see. So this is if and only if equiangular and equiareal gives isometry. So isometry happens if and only if the maps are equiangular and equiareal, right? And now you see, this is exactly what will go wrong in spherical geometry, and that's exactly also another way of stating Gauss's theorem egregium. So what happens in Gauss's theorem egregium is that you can have a map of the earth where which is equiangular. That means it gives the the directions correctly, okay, but then it will not be equiareal, okay. Or you can have a map of the earth that is equiareal, okay, but it will not be equiangular, okay. In any case, you can never draw a map which is an isometry, okay. And this is the correct way of saying that no portion of the surface of the earth can be represented by a map on a portion of the plane, which is the loose statement, okay. So so let me write this down as Gauss Theorema Egregium is can have a map of the earth, a map of a portion of the earth that is, so what I can do is I can have it equiangular, but then it will not be equiareal, but not equiareal. Then you can have it the other way around. You can have it as equiareal but not equiangular. Okay, and of course, in particular, you cannot have a map of the earth that is both equiangular and equiareal, because both equiangular and equiareal will give you an isometry. You cannot have an isometry. Cannot have a map that is both equiangular and equiareal, as it will be an isometry. So in other words, that is, you cannot have an isometry. So that's how we see it. Now, how do you appreciate this? So to appreciate this, let me tell you something interesting. We have all looked at the map of the earth, okay, right from school times, okay, and even now you look at it. Now the map of the earth that you look at, okay, everything looks fine, okay, the shapes look fine, okay, but actually it's grossly wrong, okay. The maps that we are used to, okay, when you open the world map or you have a foldable map or a map in a textbook, okay, that map is grossly wrong, okay. In what way is it grossly wrong? If you look at it, actually the shapes of the countries, etc., they will look correct, and what this is supposed to suggest is that it is actually equiangular. So what happens is that in the map, in the world map, you look at the angle, let us say